Our next speaker in the afternoon session is going to be Professor Mario Bonk from the University of Michigan. As with many of the people we've been hearing from, Mario is one of Oded's co-authors. They worked on hyperbolic geometry. Mario's going to talk to us about transboundary extremal length.
Yeah, thanks. Well, we all enjoyed these little anecdotes about Oded, so let me add just another one. So when I first came to Seattle visiting here after Oded had moved from the Weizmann Institute to Microsoft, I asked him, well, so is there a big change in your life now? You know, what are you doing? What's different? And he said, oh, well, nothing much has changed. I have a boss now, and sometimes I have to pretend that I understand what Mike Friedman is talking about. So, yeah, as it was already mentioned, I have one joint paper with Oded, and our collaboration actually also started during a hike. So it was over Wolfach conference, and well, I think this was one of the features about Oded that I liked very much. So you give him a couple of definitions, and if he gets interested in the problem, he immediately starts thinking about it. And this is also what we did in our collaboration. So it was about metric geometry, which is a little off his main area of interest. But you know, I told him a couple of basic things, and then, well, we immediately started working. Today I don't want to talk about our joint work. I rather want to talk about something that I consider one of the most important original ideas of Oded in the field of conformal geometry and classical uniformization, namely this concept of transboundary length. So I should remind you that before Oded switched to probability, he wrote a sequence of very important papers, well, in circle packings, we've heard this, but also in, well, conformal geometry and classical uniformization. In particular, there was a series of very important papers jointly with He. And I think it's fair to say that these papers, I would say, are the most important contributions to this general area, let's say, in the last 50 years or so. Okay? So there are many papers, and of course I don't have the time to talk about them all. So I just picked one little gem that I think is the most important original idea of Oded in this area, and that's the concept of what he called transboundary extremal length. So this appeared in 1995 in a paper published in the Israel Journal. The concept is a little technical, so in order to give you full appreciation of this very simple but clever idea, I first have to talk about classical modulus and extremal length. So let me start with some basic definitions. So we are on the Riemann sphere, and we have a couple of paths. So think of these paths as wires, like this. And what you would like to do is you would like to put a mass distribution on the Riemann sphere in such a way that whenever you integrate along one of these paths, the path integral over this distribution picks up at least length 1. Okay? So if this is the case for some non-negative density, then I want to call it admissible for the path family. So the modulus of the path family is now simply the infimum of the L2 norms over all admissible densities. Right? So somehow you want to spread out this density rho in an efficient way so that whenever you travel along a curve here, the curve picks up length 1, rho length 1. But you want to do it in such a way that the L2 norm, the total L2 norm of the density is as small as possible. And that's called the modulus of the curve family. Well, there's a little bit of a controversy here in this area whether one should consider this quantity the modulus, or rather its reciprocal, and work with that. So the reciprocal is called the extremal length here. So actually Oded liked extremal length, but I consider this as a little bit of a heretic view. So I rather work with modulus, and I hope to convince you in a second that actually modulus is slightly better concept, even though extremal length has a somewhat more geometric touch to it. Okay. So the most important property of modulus is its conformal invariance. So if you have a region, so if your curves sit in some region omega, and you have a conformal map applied to this region, well, then you get some image curve family that I call just f of gamma. So f of gamma just consists of all compositions of your conformal map with the paths in the family, right? I mean, these are parametrized paths. And well, one can show simply by essentially applying the transformation formula that the modulus of the image curve family is equal to the modulus of the original curve family. So this conformal invariance of modulus is very useful to explain certain properties that we all know. For example, one of the things that you all know from basic complex analysis is that if you have two annuli, let's say one with inner radius 1, the other with inner radius r, and then one with inner radius 1, outer radius r prime, well, then they are only conformally equivalent if r is equal to r prime. Okay? This can very nicely be explained by this conformal invariance modulus, namely, if you look at the curve family that connects the inner to the outer boundary, then this modulus of this curve family, gamma, is just, well, 2 pi over log r. Right? So because of conformal invariance of the modulus, so if you have this situation, well, then necessarily r has to be equal to r prime. So this quantity allows us to immediately explain such effects. Well, another effect of the same type is if you have two rectangles and you have a conformal map between two rectangles so that vertices go to vertices, well, then we all know that this can only work if the side ratio is the same, right? So if you have a conformal map like this with the property that vertices go to vertices, well, then necessarily A prime over B prime is equal to A over B. And this again can be explained by modulus because you can interpret this quantity A over B here just as the modulus of the curve family that connects the sides in a rectangle like this. Right? So if you call this curve family gamma, then you get the modulus of this curve family. Well, the reason why I think modulus is slightly better than extremal length is this subadditivity property that I wrote down here. So if you have a countable collection of curves and you all throw them together, then somehow the modulus behaves like an outer measure on the family of curves. And of course, you can write down the same quantity with extremal length, but then the interpretation is a little more contrived, right? So I think this is the main reason why one should actually work with modulus and not with extremal length. Well, there are various monotonicity properties, and I didn't write them down. Right, maybe with extremal length, you can some of them can be interpreted in a better way. One intuition that you should have about modulus is that the modulus of a curve family is a little bit like electrical conductivity if you consider the paths in your family as wires. Yeah. So then some of the monotonicity properties that you can easily prove are very obvious in this interpretation. Namely, if you have very, very long wires, well, then the conductivity should be small, and that's the same with modulus. So if you have long curves in your path family, then typically the modulus is very small. If you have many curves in your path family, well, then the modulus becomes large, right? Exactly the same as with conductivity. And if you think of this interpretation, then some of these equations that are on the board here become very intuitive. So remember, if I have a rectangle like this and I look at this path family that connects opposite sides like this, well, then I told you that the modulus of this curve family is A over B. And this ratio can easily be explained by this interpretation, right? Because if you make A larger, you get more curves. And this is why A is the numerator here. If we make b large, then the curves become longer, and this is why b is in the denominator. Okay. There's a special feature of modulus in the plane that is different from modulus in higher dimensions. The definition of modulus actually works in all dimensions, or even in general metric spaces if you have some underlying base measure. But this property that I called reciprocity here is a special feature of the plane, and there are various versions how to formulate it. So I formulated it somehow in the simplest possible context, namely for moduli that come from quadrilaterals in a similar way as this modulus that comes from a rectangle. So quadrilateral is by definition just a closed Jordan region with 4 marked vertices on the boundary. And this gives you a subdivision of this Jordan curve. And let me just denote the sides by A, B, C, and D. Okay? And what you can do then, you can consider 2 path families here, namely the path family that connects A to C and the one that connects B to D. And it turns out that these moduli are related, namely one is the reciprocal of the other. The way to prove this is actually to map the quadrilateral here to a rectangle like this, and for the rectangle case, it's obvious by this equation, right? If you take the other modulus that you get from this rectangle, well, then you get exactly the opposite ratio here. Well, if you want to apply this concept of modulus in conformal geometry, then of course you have to relate it to geometric properties, right? This is roughly the game that you play. So you have a map between 2 regions, a conformal map, and somehow you want to say something about the geometric properties of this map, and you know that this modulus is a preserved quantity. So if you can relate it somehow to geometric properties of some, let's say, a continua in the region, well, then you get some information on the map. And the nice thing about modulus is that it relates to geometric quantities. So, let me introduce some notation here. So we have a region omega. And in this region omega, we have 2 continua, so 2 compact connected sets consisting of more than 1 point. And we would like to look at this curve family that connects these 2 continua inside the region. This curve family I call gamma, E, F, omega. So it turns out that modulus is related to what I call the relative distance of these 2 continua. So the relative distance of 2 continua is just the distance of them rescaled by the smaller diameter. And one can actually show that you always get an upper bound of this type here. So the modulus of this curve family, well, I guess there's a typo here. It should be gamma of EF. This is controlled by the reciprocal of the relative distance up to a function. So this notation here means up to a monotonic function. Unfortunately, then that causes a big problem in these conformal mapping problems. You don't get an inequality in the other direction. So you cannot guarantee that the modulus is uniformly large if you have some control on the relative distance of 2 continua. This is true if the region actually is the whole Riemann sphere. But for general regions, it's not true. And intuitively, this is kind of clear, because think of a general region. Well, you will have a bunch of holes here. And if you have these holes, then you're forced to go around the obstacles. So you get less and less paths in your family. So it's clear that you cannot expect any kind of uniform bound. Okay? So that's a big problem. So modulus is unfortunately not bounded below by a quantity that just depends on the relative distance. Transboundary extremal length solves this problem. So transboundary extremal length or transboundary modulus is a quantity where you do get this uniform lower bound. And that is why this concept is so important and useful. Okay? But before I come to the definition of transboundary modulus, let me tell you a little bit about extremal densities. Okay? So what is an extremal density? Well, in the definition of modulus, we had this concept of an admissible density, and they call a density extremal, well, if it realizes the smallest possible L2 norm that I can get for an admissible density. Okay. So you can prove the existence of such extremal densities in fairly general situations, and you also get uniqueness, because it's easy to see that if you have a bunch of admissible densities for a given curve family, well, then any convex combinations of them is also admissible. And this L2 functional is strictly convex, right? From this, you immediately get some uniqueness statement for extremal densities if they exist. So more precisely, you get uniqueness almost everywhere, up to sets of measure 0. So let me tell you two instances about these two situations where you can say something about extremal densities. The first one is, again, has to do with these quadrilaterals that I talked a moment ago. So if you have a quadrilateral with these marked sides A, B, C, D, and you look at this curve family that connects A to C, well, then the extremal density is actually the derivative of the absolute value of the derivative of a conformal map that maps the quadrilateral to a rectangle, well, with the right normalization. And I guess the right normalization is that this side length here should be 1, and of course corners should go to corners. Okay. Similar results also holds in the multiply connected situation. So suppose we have the same picture, but now we have a bunch of holes here. And again, you can ask yourself, well, what's the extremal density for the path family that stays inside the region but avoids the holes? And this is actually very interesting. It turns out that the extremal density comes from a conformal map of this quadrilateral to a rectangle with slits removed. So the extremal density is, again, just the absolute value of the derivative of a conformal map. Well, maybe I should push this a little higher. Yeah, where you have slits like this removed. And that's actually very useful if you want to map an arbitrary region to some kind of a normal domain. And well, there's a classical theorem that actually goes back more than 100 years to the times of Hilbert. So he had an argument to show that every region, whatever the connectivity, can be connected to what we now call a slit region, namely a region where slits are removed in a similar way like this. And from what I just told you, it's very easy to understand why this is not so hard to prove, because you have a natural extremal problem whose solution actually is related to the conformal map. Right? So one way to prove this fact about uniformizations of arbitrary domains by slit domains is just to look at your domain, introduce a picture like this, then consider the modulus of this path family here, look at the extremal row, and then well, try to cook up the map actually from the row. That's one venue. Well, there's a famous problem that is more than 100 years old in this area that is still unsolved, and that's Köbes Kreisnormierungsproblem. And well, it uses as normalizing regions the so-called circle domains. So by definition, a circle domain is just a domain in the Riemann sphere whose complementary components are round disks. And Köbe in 1908 asked whether every region in the plane is actually conformally equivalent to one of these circle domains, so a domain where you have holes that are round disks. And he actually proved this in 1920 for the finitely connected case. That's a very important and useful uniformization theorem. If you have a finitely connected domain, so if you only have finitely many holes in your domains, if you have a situation like this, well, then there's a conformal map onto something that looks like this, where all these boundaries here are just circles. One big advance in this area is a theorem to He and Oded from the early 90s. Namely, they showed this in the case that you actually have countably many components. And that was a big progress in the area. And the original proof actually was by using ideas from circle packings. But later on, Oded actually found a different proof by using, well, this transboundary, extremal transboundary length that I will introduce in a moment. But before I do this, let us think why this problem is so hard. Well, the reason for this is that there's somehow no natural extremal problem that you can solve, and to solution would somehow be related to a conformal map onto such a circle domain. So I think the main observation that Oded made is that if you change the geometry of these holes to slightly different shapes, actually then you do get some extremal problem that is very natural. And the shapes that occur in these pictures are actually squares. Okay? And that has to do now with this, what I call the transboundary modulus. So if you see the definition for the first time, it's a little technical, but let me try to explain it maybe here on this other board. So again, you have a domain, and you have a bunch of holes. So I guess I called them K, J. There could be even countably many, but let's not make things too complicated here. So you have a domain omega, with these complementary components, and you have a path family. And the path family is actually allowed to travel through these holes here. What you would like to do is you would, again, like to associate a quantity to this path family that is very similar to classical modulus. And again, you will have some a continuous density here, this rho that actually lives on the region, but then you have extra terms, and that's the main point. These extra terms actually live on the holes, right? So you assign to each of these holes here a discrete quantity, rho 1, rho 2, rho 3, and so on. And now the admissibility condition is essentially the obvious thing. So you integrate your curve here along this continuous part of the density. This is this term here. In addition to this, you pick up a row from each of the holes that you meet. Okay, and if this sum is greater or equal 1, then you call, well, this density consisting of a continuous and a discrete part admissible. Yeah, so in some sense, the curves you can travel through a hole by paying a flat rate. Yeah, so flat taxi rate, it doesn't matter, whether you hit the hole several times. If you use it once, well, you pay your rho I, and well, it goes into this admissibility condition like this. And well, then again, you try to look at a certain infimum, and it's kind of clear what you want to infimize. You want to infimize the analog of the L2 norm here, right? So just the L2 norm of the continuous part plus, the natural sum that comes out of the discrete part. The funny thing here is this quantity, even though it uses things that are not in the domain, is still conformally invariant under maps of the domain. That makes it actually so useful. So this is this conformal invariant. Actually, Oded formulated it a little differently. So he introduced some quotient space where he actually punched the hole to one point. But let me not do this like this. Let me do it a little simpler. So this conformal invariance here says that if you have any homomorphism on the sphere that is conformal on the domain, so no requirement whatsoever on the holes, then you actually do get this conformal invariance of transboundary modulus. The proof is almost a triviality. So for the continuous part, you do, again, the same transformation formula as you did for classical modulus. And well, the other thing that you use is that somehow in any conformal map, these holes are somehow shuffled around, even though the map is not defined. Right? I mean, to make this rigorous, you can talk about the end compactification or something like this. But it's essentially clear that you just shuffle around these discrete weights, and well, then you get this invariance. Well, I'm running out of time, so let me quickly say what you can do with this. And somehow you get some intuition of what is going on if you just look at extremal densities. Namely, if you, again, have some quadrilateral, some marked corners, you have some holes here. And you look at the path family that connects the sides of the quadrilateral. Yeah, they are allowed to actually hit the holes. then the extremal density here of the transboundary density has a continuous part, which is, again, just the derivative, the absolute value of the derivative of a conformal map onto a rectangle with these squares removed. And the discrete parts are just the side lengths of the squares. Right? So the extremal row j's here correspond to the side length of the jth square. Okay? And once you see this, I mean, then you know that this is very useful for some conformal mapping problems. Yeah, let me just give you one quick theorem that Oded proved using this concept that has to do with, well, what he called fat sets and co-fat regions. So what is a fat set? So fat set is a set with the property that if you place any point in the set and you look at a ball centered at this point of a radius whose diameter is not too large, let's say, well, less than the diameter of the set, then the percentage that you see here that is eaten by the intersection of the ball and the set is fixed for every such ball, right? So this is what I call tau. So if you look at the ratio of the area of the intersection to the area of the whole ball, well, then you get this fixed percentage tau. And well, a co-fat region now is just a region whose complementary components are fat in this sense or are just singletons. Okay, so this is what Oded called a co-fat region. And the important thing about transboundary modulus now is that in contrast to classical modulus, you do get uniform lower bounds for moduli of path families connecting to continua, just depending on the relative distance of these continua. And this somehow allows you to play the usual game. I mean, you use the conformal invariance, you have lower bounds of the modulus for path families in your source domain. Well, you have upper bounds in your target, and you can use this to your advantage to, for example, prove this theorem that is due to Oded. If you have any co-fat domain, then you can actually conformally map it to a circle domain. That's a very nice theorem. So what this essentially says is that, well, if you want to solve Kurbis conjecture, it doesn't really matter whether you map to a circle domain or, for example, to a domain whose complementary components are squares, right? Because squares are also uniformly fat. So you can essentially choose your favorite domain and solve the problem there. So yeah, I think I stop here.
Question?
What's the obstacle using these methods to prove the full Kurbis conjecture?
Well, that's a difficult story. So essentially, somehow you lose all control. So for example, if you had some uniform continuity in the map, right, I mean, then you could just go from the finite case by some limiting argument to the infinite case. I mean, the case of infinitely many connected components. But unfortunately, you don't have this kind of control. So the whole game really is to get this type of control. And you can get such a control in the case where you have countably many connected components. There, this kind of naive approach works. But in the general case, unfortunately, it doesn't.
Other questions? Okay, please join me in thanking. It's a great pleasure to introduce Greg Lawler from the University of Chicago. Greg is a long-time and very distinguished contributor to probability theory. And in the context of this conference, of course, some of the Oded's most famous and most groundbreaking work was done in collaboration with Greg and with Wendelin. Greg is going to speak to us today about something different from what's in the program. It's path properties of Schramm-Loeffner evolution.
Okay, thank you very much. I'm very happy to have an invitation here. Like many people in this room, my personal research has been changed greatly by the insights of Oded Schramm. And I'd like to focus on some of the ideas that Oded have done that have particularly influenced me, and that's this beautiful object, which we now call the Schramm-Loeffner evolution. We've already had an introduction to this in Vendelin's talks. I'm assuming that talk is a prerequisite to this talk. And we're going to build from there. So to recall, what Oded did was looking at scaling limits of various things, particularly the loop race walk at the time. And what he did was, he thought, suppose there's a conformally invariant limit that satisfies a certain Markov property we know it should satisfy. What would it have to be? And as we've now learned, he then rediscovered the Loebner equation, wrote down the Loebner equation, then figured out basically that it would have to be the Loebner equation with a Brownian motion input. And that's part of his original paper in from the Israel Journal that Vendelin talked about. So if there's a limit, he ended up with an equation like this. I've written it a little bit differently than normally done. I'm in the upper half plane, so z is in the upper half plane. I didn't write that there. I should say that there was also an observation of Oded that for a lot of the properties, although most of the Loebner equations written in the disk or the complement of the disk in the complex variables literature, it's actually easier for a lot of the properties to actually look at it in the upper half plane. And in particular, the Poisson kernel, which basically drives the Loebner equation, is easier in the upper half plane. So we basically have this equation in the upper half plane, where gt is a function. Ut is a function on the real line in this case, a continuous function on the real line. And a is a parameter we can play with. Now, the way Oded and most people do it, they tend to make a equal 2, and they do more variation here. But just because the way I tend to make this a Brownian motion of variance 1 and vary this, it's just a constant linear time change, doesn't make any difference. But if you see a, wherever you see a's in this talk, a is equal to 2 over kappa, and that's consistent. So you just see if you ever see it there. But the question is, now that you know it's got to satisfy this, well, are there things that satisfy this? Well, if I stick in any continuous function here, then this equation has a well-defined solution up to a certain time. And it's not too difficult, a little bit of work to show that, in fact, if for any time t, the solution of this will actually be a conformal map from some subdomain of some unbounded subdomain of the complex plane to the complex plane with a certain boundary behavior at infinity. It looks like the identity at infinity, the next term, the constant term is 0, and then there's another term which is 1 over z. That a is the same as this a. It comes from the rate here. And then you have corrections. Oops. Well, there should be a t. That's typo. There should be a times t. Thank you. There should be. But the question is, but just because we have this unbounded domain ht, that doesn't necessarily mean that it comes from a curve. So the questions that I'm going to deal with is some of the basic questions. Does there exist a curve, gamma, such that ht is the unbounded component of h? So remember that Oded originally was looking at random curves. So this should be coming from a curve, but it's not so obvious to see what's happening with that curve. Is the curve simple, i.e. non-self-intersecting? Does it stay in the upper half plane? Those are really turn out to be essentially equivalent questions. And finally, what's the Hausdorff dimension of this curve? These are actually going to be fractal curves. The main paper of Oded's that I'm going to work on is a paper of Oded and Stefan, and I actually thank Stefan for not speaking about this, which means I can speak about this. But the main thing is basic properties of SLE. Now, it was finally published in 2005. The earlier versions of this, I actually once talked to Stefan and I told him how much I liked the paper, but I really, after struggling with it, thought basic properties of SLE was kind of the wrong title. But now that I think about it now, I think it's the right title. And these really are basic properties of SLE. So I even agree with the title of this paper. So let's talk about existence of the path. And I didn't draw any pictures here, so I just have a simple picture here. So this is what we're thinking the curve should look like. So that's assuming it was a curve. GT is mapping the curve back to the upper half plane. And this point gamma t should be mapping to this point u sub t, which is the u sub t in the equation. So if I want an equation for gamma t, since that should be mapping there, so ut should just be gt inverse, or if I write ft for gt inverse, ft of ut should be gamma t. So there we go. That's the curve. Gamma t equals gt inverse. The only problem is that when you have rough boundaries for conformal maps, these things may not exist. This could be a very, offhand, could be very, very rough. And in fact, one can actually find out that there are, the solutions to the Lorber equation might not come from curves. Let me just go back to the equation. So there's the equation up there. This is dying. Okay, well, look at the equation up there. The behavior of that equation does depend on u sub t, and there's various work in the deterministic world. I mean, there's Don Marshall, Stefan Roda, Joan Lind, and some other people as well. I'm sorry if I'm... but what happens with this equation, if you look at it, if you've never seen it very quickly, what happens is this slit here tends to grow in time t. This slit tends to grow about delta t, what's called Brownian scaling. So if I just fixed a growing point there, this would grow at about delta t. So what keeps this from being a curve is that this starts moving faster than it's growing in this direction. When this thing moves square root delta t or more in a certain direction, then you might be in trouble. And that tells you to some extent that the natural borderline for this would be UTs that are Hurlder continuous of order 1/2. And in fact, if UT up here were Hurlder continuous of order 1/2, then you can actually show that if A is large enough, this actually gives you a simple curve. That's actually what they showed, what they showed. But there are examples of Hurlder continuous functions order 1/2 and small a such that you don't have them. Now, a Brownian motion path, u sub t, is not Hurlder continuous of order 1/2. But in some sense, it's randomly Hurlder continuous of order 1/2. It's like it's Hurlder continuous of order 1/2, but the constant is random on different scales. So you can sort of think of it as a question. So it's not clear there whether or not it's going to exist, but if it's going to, we would like to do that. So how do we try to prove this? Well, we just approximate. We'll let gamma n of t approximate it by, instead of evaluating ut at ut plus I times n, that's well defined. Just move it up a little bit here. It's certainly defined there. And then just take the limit. Okay. So the question is, can you show this limit exists? And then once you show the limit exists, can you give bounds on gamma s minus gamma t to show that you actually get a continuous curve? Well, if you just think about it, say gamma t minus gamma n t is just less. If I go along here and take its image over here and get the length there, all I have to do is look at the derivative of the map. So, thank you. That's a good chairman. Okay, so to get this, to be more precise, what I should say is that if this integral is finite, then I'll be able to define gamma t such that that's true. If this integral is infinite, then I may not be able to define a limiting value of gamma t. But you actually get this thing. So there's the quantity to start estimating. So if one can show that this derivative is such that it's bounded, say, less than y to the delta minus 1 for some delta bigger than 0, then in fact we get this. Actually, this is almost true deterministically. Deterministically, you basically get y to the minus 1. That's the worst that you can get. However, y to the minus 1 is not good enough to make this integral converge. So you need something better than that. Okay, now there's a technical difficulty if you're dealing with very wild u sub t's, that you have to do this for every possible value of t. But for Brownian motion, we have this approximate Hölder continuity. And basically, with the Hölder continuity, that says I don't have to take every t. I have to take just maybe, if I'm taking n here, then I only have to do n squared values there, the integers. 10 years ago, I knew very little about, say, complex variables too. When it comes to conformal maps now, I've found out how much you can do with just a couple of tools. So know the distortion theorem, know the Kirby 1/4 theorem, know the Berling estimates. You hardly need to know anything else. That's but you need to know those. Okay, so that's at 1t. And now, what happens if you do other t's? Well, now we just basically do here a triangle inequality. So fs hat is well, okay, you can just go up here. So that's the approximation at s, the approximation at t, and we just split it into two pieces because we have s's appearing two places. So we just take one of the s's and one of the other s's. And as it turns out, if I fix a point and I want to vary s and t, that's no problem. This difference in this derivative is of the order of this for s and t small. I'm not going to go through proof. I'll just say this is just deterministically from the Leibniz equation, from the differential equation. Holds for every path. And now if I want to compare ft I epsilon plus us I epsilon plus ut, so this is with the same function, but two different points, that's where the distortion estimates are. And when you do that, and now if I use the Hölder continuity, I get this. So basically, this difference is okay. And so we get sort of this. So let me just jump. So if I'm taking gamma s minus gamma t, there are three terms here, but basically the gamma ns minus gamma nt turns out not to take too much work. So it's mainly the gamma s minus gamma ns, gamma nt minus gamma t. Those are the ones that have to be handled. And to handle this, by this, is basically, can I handle the derivative? So how do I get estimates of this derivative? And now, so far we haven't used any probability at all except for the modulus of continuity of Brownian motion. So now what I need to do is look at this function. And also in the Oded and Schramm paper, they showed, and this is actually not difficult, use the fact that just deterministically this function, which is an inverse, has the same distribution as a Leibniz equation with reverse time, or a Leibniz equation in the reverse direction. So this is the same equation we had before, except we have a minus sign in the denominator. So if I want to take moments of this, it's the same thing as taking moments of this. So how do I do this? Well, there's a few different equivalent ways of finding moments. You can either you talk about writing second-order differential equations or things like that. I prefer now to talk about it in terms of what's the appropriate martingale or local martingale. So in this particular case, if I take let mt of zb, ht prime lambda, okay, ht lambda, that's just the imaginary part of the image, signed to the minus r. Don't even think too much about this, but it's just a computation that if I choose these parameters correctly with respect to each other, I can choose r to be whatever I want. Then in fact, this is a martingale. This is Ito's formula. It's just an application of Ito's formula. And therefore, the expected value of this, let's take z to be I. The expected value of this is 1. Well, if I didn't worry about correlations here, this is the reverse flow. The image of this grows like t to the 1/2. And if things don't skew very much, and I stay to the middle and don't hug the boundary, that should be of order 1. So this guy should be order 1 times t to the zeta over 2 times that, and you actually get this estimate. And that's actually giving you the moment that you want. Let me just say this isn't true always. You have to put some restrictions on R. And this calculation, but don't want to go through the calculations. But I'll just say, once you have this, this estimate is good enough to prove existence of the curve for kappa not equal to 8. And this is essentially the proof in the Schramm paper. For kappa equals 8, what I've done here is not good enough to do things. The existence of the curve follows separately from work. This is a joint paper. But like many of the results in joint papers, this really should have the S circled on it as a Schramm result. So if you talk about for kappa equals 8, how to prove that SLE kappa really approaches SLE 8, or the uniform spanning tree approaches SLE 8 sufficiently closely to derive this is okay. So we know now we know it's true for kappa equals 8. Actually, when you do this, you also get a guess for what the Hölder continuity is. And in fact, that's now a theorem, and I like to say. In fact, you can actually find what the Hölder continuity of gamma is. Let's say for t away from 0, t equals 0 is different. And there's the formula. It actually turns out to be not particularly nice, but in some sense that's because this capacity parameterization of the curve is not very natural. But there is one thing, if you just want to plug it in to note for yourself, is that you have it is Hölder continuous with a positive number if kappa is not equal to 8. If kappa is equal to 8, in fact, it's now a theorem that the curve is not Hölder continuous of any alpha bigger than 0. Now, an open problem, I think still open, is to find a different proof for kappa equals 8, which follows this line, but is much more careful and handles all the logarithms correctly. But we will talk about that too. Okay. But that gives the curve. Okay, so that's the existence of the curve. Now I want to talk about the dimension of the curve. And this is just some notation. I'm defining it, so I'm going to define conformal radius. Actually, just for convenience, I'm going to do 1/2 conformal radius. So if I have a simply connected domain D and a point W in it, this will be 1/2 f prime of 0, where f is the map from the unit disk into D from taking 0 to W. The factor 1/2 is just, I like gamma of the half plane at I to be 1. Oh, that's actually an upsilon. Sorry, it's upsilon. But the reason to put this is, conformal radius turns out to be something more interesting or easier to deal with than distance from W to the boundary. They're actually comparable quantities. So in many ways, I really want to look about the distance from a point to the boundary, but it's comparable to this conformal radius. That's the Kirby 1/4 theorem. Let me just. I'm also going to give some formulas. I just want to give some notation. So if I have a simply connected domain and I have 2 boundary points, I can talk about the argument of a point W with respect on the inside with respect to those 2 points. And it's just the argument that you would get if you map it to the upper half plane. And I'm actually, S will be the sign of the argument. So if it's in the upper half plane and I've got a point, I'm just looking at the sign of the angle of the point. And for other domains, the conformally version of this. Okay, so that's just notation. Okay, actually, well, maybe I'll do this. Okay. We first might ask the question, do we hit W? Okay, maybe we'd ask the question, does this curve actually hit W? Well, what you do is, in that case, if you want to know whether something hits W, you take the Lerner equation, but you change the parameterization so that it's parameterized by this conformal radius, which decreases. Or we can call this the radial parameterization. It's actually the parameterization of radial SLE. And if you look at it and see what happens to this angle, you get an equation like this. So this is the angle at W, some point on the inside. And now as we see what happens, this is now a fairly simple differential equation. Cotangent tangent theta tilde looks like more or less 1 over theta tilde. The question is, what happens? Does this reach the origin? If I'm going to hit a point, then as I get close to that point, the angle keeps fluctuating. However, if I miss a point, then this thing disappears. And it turns out, using this, you can see that for kappa bigger than or equal to 8, the SLE curve actually hits points. Just for SLE, for kappa less than 8, SLE does not hit points. And this equation also, and this actually goes back to Oded's first paper, for kappa less than 8, you can actually use this equation to determine whether the curve goes to the right or the left of W. I won't prove it here, but something for kappa less than or equal to 4, you actually get that the paths are simple. For kappa between 4 and 8, they're not simple. But I won't do that because I want to discuss a little bit about the fractal dimension. So how do you determine the dimension of a curve? I mean, when I started working on SLE, and this was very new, it was very hard to work on. I had techniques to work with Brownian motions. But SLE, what you're doing is you're looking at the evolution of a curve by measuring its effect on points away from the curve, not by the curve itself. There's not an equation on the curve itself. So how do you find, like, what's the fractal dimension of the curve? Well, if I want to find out the fractal dimension, you might ask, well, how many balls of radius epsilon are needed to cover a curve? If I want to know how many balls of radius epsilon are needed, what I can do is I take a particular point, W, and ask what's the probability that the curve gets within distance epsilon of W. And at least heuristically, in terms of expectations, that should behave like epsilon to the 2 minus d, where d here denotes the fractal dimension of the curve. Since this is distance, I could replace the distance, and this is with the conformal radius. What's the probability the conformal radius looks like that? So how do you compute this? Well, let's think about this. Suppose there were a function, which I think of as a Green's function. Think of this roughly as speaking. What's the probability that an SLE in the domain D from Z1 to Z2 gets close to W? So the probability that the distance is less than epsilon should look like epsilon to the 2 minus d times this thing, this sort of Green's function, which has to do with the domain. Well, there's a certain scaling rule, but just because of the way we have this epsilon here, if I take a conformal transformation, this epsilon to the 2 minus d means that this thing should conform like this, to transform like this. And the other fact, which is basically very simple idea, if I'm looking at this point right here, and I say, just think, what's the probability I get to that point? Well, you can ask, what's the probability I get to this point given I've seen the curve so far? Well, as I move this curve, the probability of getting there given the curve so far should be a martingale, or at least a local martingale. I'm not going to worry about that distinction. So, and what's the probability? And once I've gotten this far, well, here, now my new domain is d minus gamma 0 t. This really should be if this is right if gamma is a simple curve. A little more complicated if gamma is not a simple curve. Basically, look at the domain I'm in right now. We're now going from gamma t to z2. What's that? And that needs to be a local martingale. So that plugs in Ito's formula. And if you just plug into Ito's formula, you actually get, and this is done in Schramm, that the dimension has to be 1 plus kappa over 8. And you actually get the Green's function as well. Well, they didn't use that term. This function can be found in their paper. And it's just the formal radius to a power times the sine to a power. Sine to a positive power. And so this actually, you find the beautiful result is that for dimensions between 1 and 2, Hausdorff dimensions strictly between 1 and 2, there's only one value of kappa that corresponds to it. So it's a 1-to-1 relationship between dimension and kappa up until we saturate at kappa equals 8. Okay, maybe I'm running a little short on time. I can say you can improve on this and actually show that the probability of that, but maybe I will skip that because I want to say a little bit about this slide. So one beautiful thing but disadvantage of this is that it's focusing on one point. It's giving one point estimates. There's another question about second moment estimates. So for those who know about dimension, what Stefan and Oded showed in their paper was they gave an upper bound for the Hausdorff dimension and gave good heuristics for the lower bound, but did not prove the lower bound. To prove the lower bound, there's a standard technique for proving the lower bound, which in this case requires a certain second moment estimate. This was not done by Stefan and Oded, but it was done later by Vincent Bafara. Now, I will say that this is much harder to prove, and it's kind of unnatural. And well, I'll just say there were some problems with early versions of this paper, Vincent. And in order just to give a little credit, I do think Oded was one of the people responsible to put it in helping to get this thing to. But it's now published by Fire, and this certainly is correct. There's another alternative proof which can be given using the reverse Loeffner flow, for which the second. So we actually have that the Hausdorff dimension is like that. And actually, maybe I will skip that because I'm nearing the end. Let me just emphasize again here how what's very unnatural to me 10 years when Oded was first doing this, and by the time Oded had shown this to me or to Wendel and me, Oded already had some experience with this, how you show something about a curve by looking at what happens away from the curve. When I've given colloquia on SLE, the question I always get at the end is, what about 3 dimensions? I even answered it. So what you can do in this curve, this equation really has 2 things in it. One is true for 3 dimensions, and that is that if you want to observe a curve, you can actually look at a point away from it and see the effect of that point away from it and make it a differentiable, smooth function of that. That's doable. However, what's also true in here is, in 2 dimensions, is you have conformal invariance of all these harmonic functions. And that's not true in 3 dimensions. So that this really combines both of them when you do this. Okay, I think I've used up my time here.
Thank you, Greg. We have time for questions. What about 4 dimensions? Yes?
So one problem with 3 dimensions is already, I find it, the longer I work on this, the harder I find it already that the set exists. In 2 dimensions, even that this curve that you discussed is even the non-empty set. So in higher dimensions, I think it is possible. We haven't worked out the details, but that we discussed that there are continuous driving terms in 2 dimensions that create nothing in higher dimensions. So you have a flow that is exactly the analog of the Loeffner equation. So things flow down in an upper 3
But
states.
It's not a flow of conformal maps.
Well, of course not. So it's a flow. It's a sort of the natural thing. It's in each slice.
And isn't that more natural to have a flow of metrics in 3 dimensions?
Well, if I can comment on your comment, just to explain my final comment, what I call the Loeffner equation, or is a weaker thing than what you were probably saying. So, like for 2 dimensions, the Loeffner equation is something is for the flow of conformal maps. But you can think of it as 2 steps. One is a flow on the potential that's going on, and the other is the piece that makes it a conformal map. And if you're only looking at the part on the potential without mapping it any place. That's actually what I was talking about with a learner. Sort of the hitting probability for a particular point.
Okay, I think coffee's here, so please join me in thanking both speakers from the session.